about momentum, and because momentum is primarily focused around collisions, it's as you remember, energy conservation is when the system is isolated. If you're colliding with something, you are inherently not in an isolated system unless all the collisions are contained within your system, okay? So as long as you're considering a system to be something like a ball, collisions mean that you're not necessarily conserving energy, but momentum is conserved for collisions, okay? So just to go over what we'll talk about, we have momentum and impulse. We're going to define those things. Then we'll talk about conservation of momentum. We'll talk about the different kinds of collisions, starting with elastic collisions. Then we'll start introducing center of mass, and if we have time, we'll go into rocket propulsion. I think we will probably do it no matter what, since we're doing these rocket labs. I usually treat it as more optional, but if we're going to launch rockets, we should probably know how they work. So let's talk about momentum and impulse, and here we're just starting with some new definitions. So here's another would you rather situation. Would you rather collide with a tank or a very small tricycle? What? You're just standing there. But okay, so there seems like there's an obvious answer to this, but there's one question you should ask.
How fast is it going?
How fast is it going, right? If you get hit with a tank, but it's not moving very fast, it won't feel great, but you probably won't die.
I don't know, I've seen Tiananmen Square.
Well, it doesn't have to be going very fast. Yeah. Ugh. Don't Google that if you want to value your emotional well-being. But it does depend on speed. This thing mostly isn't going to hurt you at low speeds, but if it's going 100 miles per hour, it's still going to do some damage, okay? So the other thing, let's say, should you be afraid to catch a ball going 45 meters per second, which is about 100 miles per hour with no glove? This is a question I ask myself often with my 9-year-old who's getting good at throwing. He doesn't throw that fast, but it's starting to feel like it. So what question should you be asking about this?
How long does it take to slow down?
How far away? Actually,
What kind of ball is it, right? And specifically, what kind of ball, what mass is the ball, okay? Because remember, getting hit with a ping pong ball at 100 miles per hour will hurt, but getting hit with a bowling ball at 100 miles per hour is going to do more than hurt, okay? You may not recover from that. So it really depends on the mass. And the reason we're going through this silly what-if scenario is because momentum, because of this, includes, is a useful quantity because it includes both mass and velocity. And I say velocity instead of speed because it's still a vector, okay? And so remember, this is the 3 equal sign, which means this is a definition. So momentum is defined as the mass times the velocity. And momentum has the same direction as the velocity. So that means you can break it into x, y, and z, or r, theta, z, or whatever 3-dimensional spatial units you want to use. And it has the terrible, not very informative units of kilograms meter per second, okay, which is, they didn't even come up with a new unit for it. It's just smashed together units from mass and velocity. So apologies there. As we know, momentum should be parallel to whatever the velocity vector is, but the size of the vector gets adjusted by the mass, okay? So your momentum vector can be bigger or smaller depending on how big your object is, how massive your object is. And the other thing about it being a vector is the direction's gonna matter now, okay? Remember when we were talking about kinetic energy, we were talking about speed, and it didn't matter if something was going up or down, it had the same kinetic energy. Okay, with momentum, you're going to have to keep track of signs and vectors again. So here is a question we'll start out with. Okay, it's either B or D. We got some B's and D's in the chat. Please discuss. We'll vote again. Oh now more thinking, the more we think about it, the more we don't know, and that's true. There's actually not enough information because, remember, one of them is 1/2 mv squared and one of them is mv. As you adjust to the mass and velocity, you can get very different things by not squaring this. So you really need to know more information in order to figure out if these two things are equal or variable in this way. Okay, more importantly, because of direction, let's try this one out. Okay, it's one of these things. Please talk about this, we'll vote again.
So is it negative 20 to 10?
So it's either depending on how you set up
Is that what you picked?
That makes it hard.
What'd you pick?
I picked
But it's talking about change of
Why?
momentum, so at the beginning it starts at,
It's the mass she says is
say
it went
negative
2 meters per second one way.
and then
So if you
the final
and then it went one
is
one
10.
way, all you really lost is
Oh, wow, we're tied between A and C, even in the chat. So we will set this up, okay? Because remember, we actually know how to define momentum. I'm not even gonna try with that. Okay, so change in momentum, okay? That's going to be momentum final minus momentum initial, okay? Then momentum final is what? 10 times 1 meter per second minus, right? 10 times negative 2 meters per second, okay? So that's gonna be 10 minus negative, what's minus a negative? Plus. So 10 minus negative 20 should give us 30 kilograms meters per second. And this is what I mean by the direction matters, right? These are vectors, so positive and negative direction matters. And because it's a change in momentum, it actually doesn't really matter what happens in between here and here. It just matters where you start and where you end. That's your change in momentum, right? So your final minus your initial. So the answer is going to be A. And let's talk about how this relates to force, okay? So how do we change momentum? What does it mean to change momentum? What are we changing?
change mass or velocity. So
Yeah.
the acceleration if you're changing velocity.
Changing, it's an acceleration, right? So there's a force involved. We're changing both speed and direction for the most part. So that means we're probably changing acceleration. So if we go back to force, we can rewrite force in terms of momentum. And this is sort of a fun math issue. This thing has lost me. Okay, because remember, we're writing this as force is equal to mass times acceleration. What do we know about acceleration? Well, that's gonna be the same as dv dt, okay? So really what we're doing is we're just saying d, we can pull the m in, it's constant, mv dt, that's the same thing, that becomes d momentum dt. Okay, so this is really just the same as Newton's second law, but written in a derivative form, okay? So remember, but what this tells us, why it's even useful to write this way, is that the net force on an object determines the change in momentum. Okay, just like it determines mass times acceleration, but it's useful because of the way that we use it, okay? And one of the big things that we now have access to is changing force, because before we were primarily talking about force diagrams with constant force. We just added the ability to sort of integrate force when we're talking about work. But remember, the net force on the object changes, okay, during a collision, and collisions are special this way. And for this section, the slow-mo guys are very useful, but I just used a lot of GIFs? I think it's GIFs. Anyway, if you want to plot the force on this tennis ball during this collision, what's it going to look like? You just plot force over time. So right when they impact, is there a lot of force? Like right when the tennis ball hits the right when the racket hits the ball, is there a lot of force? Where is the most force happening?
When the ball's squished.
When the ball is squished, okay? So unsquished ball, less force, squished ball, more force. So that means you start with a little bit of force, you go up to a maximum, and then as the ball starts moving away, it goes down again. So if you want to graph the force over time, it looks something like this. It's approximately Gaussian, okay? So if you plot this on a graph, this is force versus time. Okay, previously we had force graphs, but what was it versus? We had a lot of graphs of force versus something when we talked about energy. Yeah, it was force versus distance, right? And if you take the integral of that, what do you get? Work, okay? Imagine if you take the integral of this, what do you think you're gonna get? Momentum or impulse, right? We'll talk about impulse in a minute, but they're very closely related. So the way this breaks down is contact begins right about here. You start having a very small amount of force. There's this compression stage, right? This is the maximum compression up here. And then you have expansion as the ball starts to rebound back. And then, you know, your contact ends, okay? So anytime the ball is not in contact with the racket, what's the force? 0, right? They're not touching. But during this contact period, this is a non-trivial amount of change, all right? This force becomes very big and very small very quickly. This is our time change, and if you look at this, the area under this curve has a physical meaning. It's going to be impulse, okay? And we'll talk about impulse in a second, but it turns out impulse is equal to change of momentum, so it's related to momentum, okay? So for momentum in a non-isolated system, meaning there's stuff outside, the change in momentum of a particle is equal to the impulse. So remember, change in momentum, that's momentum final minus momentum initial, should be equal to this impulse, which is that area under the curve of the force versus time graph, okay? And it turns out from the perspective of this car, it doesn't really matter if it's hitting a wall or another car. As long as you have this nice symmetry, you get about the same impulse, okay? Okay, so the impulse is the capability of a force to change momentum. And so if we look at this graph again, right, we have this varying in time, so we have force over time, and our impulse is just the integral of this graph, okay? That's very simple theoretically. It turns out in real life often it's hard to measure the force over such short time periods. And also impulse also has the same units as momentum, kilograms, meters per second. But we often end up doing something like estimating the impulse, where we just sort of take an equivalent area. So we take the average force and we multiply it by the time of contact, and it gives us about the same thing. You'll see when we do the lab that our measurement device for force is not very precise, meaning it doesn't sample fast enough to catch the force. So it kind of just like, it looks just like a blip, right? You don't get this whole curve, even though that's what's happening. And so depending on how good your force measurement device is, you don't always get the whole nice curve. You just get like a little bit of information and you kind of just guess, okay? Okay, so here, so remember, momentum, change in momentum is equal to impulse. Okay, which just means if you have more force over time, you have a bigger change in momentum, which should make sense, right? More force, more acceleration, that means you're changing your speed, and it's dependent on the mass, okay? So we want to know which of these has the greatest capability to change the momentum of your object. And so we're basically asking for the largest what? Impulse. Okay, so try that out. An A or B, please discuss, we'll vote again.
What?
Impulse is the area underneath the curve, right?
Yeah.
Both of those, which one has a bigger area? The triangle or the rectangle?
That's
Oh, yeah.
True.
So like force is 100.
It's just so that'd be one space over the span of
Okay. So we're just looking for the biggest area under the curve. What's the area of this?
100.
50.
50, because it's a triangle, so 1/2 base times height. Base is 1, height is 100, but there's a half in there, so that's 50. What's the area under this curve?
100.
100, so 100 bigger than 50, so this is our winner so far. What's the area under this curve?
3.
3, yeah, that's smaller than 100. Yes, okay. Area under this curve?
Less than 18.
Yes, 8. It's at 10 to 20-ish, but still less than 100. So our best answer is going to be B, just a short quiz in geometry, okay? But the key thing here is we're looking for the impulse. And the impulse doesn't have to be a large amount of force over a short time. It can also be a small amount of force over a long time because it's the area under the curve. So the impulse of a small force that's constantly pushing, right? I don't know how many of you you heard of like an impulse engine? I think this is mostly in sci-fi, but occasionally it shows up in the real world. Basically, if you just have a small amount of force, that's a constant acceleration. You can get up to really high speeds over a long period of time. So, you know, I think if there's like some rocket ship video games that like base their whole premise off of this. But this is a small force over a long time. This is a very large force over a very short time. They end up being sort of equivalent, okay?
Isn't that what they want to make spaceships out of? With like fusion and stuff like that? Making them pulse?
Yeah. I think they talk a lot about that in the constant acceleration engine in like The Martian. He does all the math for you too, which is nice. That's like some sort of nerdy physics porn book. But anyway, okay, so let's talk about impulse momentum theory. So once again, now remember I told you golf balls are springier than they look. Here's a slow motion video of a golf ball. So this golf ball is impacting. What do you notice about the momentum of this golf ball? What's its initial momentum? Positive or negative? Positive, right? It has a speed going this direction and it's the mass of a golf ball, okay? After it hits the wall, it has pretty much the same momentum but going in the opposite direction, okay? During contact, it's gonna have impulse. So if you wanna plot this on graphs, we'll plot first our impulse, which is only happening while these things are in contact. So you should have 0 force, right? As it's moving to the side, then as it's in contact, you'll have a force pointing that way, and then you'll have a change in direction, okay? So if you wanna plot this out, you can see your force is 0 until it starts to make contact with the wall. Then it's going to go negative. Why is it negative? Well, we picked this direction to be positive. That means the force of the wall points this way, which would be negative, okay? So it's a negative force, which gives you a negative impulse because the area under the curve should be negative in this case. You can see the momentum starts out constant. It's a constant positive momentum. During this time when it's interacting with the force, you change it till it completely stops, turns around, and then you get a negative impulse in the other direction, a negative momentum in the other direction. If you want the impulse, you just take the area under that curve, okay? And so this is the definition of impulse momentum theory. The change in momentum, meaning if you take these two things and subtract them, should be equal to the impulse, which is the area under this graph. Okay, so this is my full visualization of impulse momentum theory. Oh, including this cool arrow that looks like this. Okay, let's try another problem using impulse momentum theory. I'm very proud of that slide. It's like it's A or D or B or C. Okay, please discuss. We'll vote again. Ooh, we've moved towards the correct answer. So the answer is going to be A, but let's talk about what's happening here. Remember, the impulse is the change in momentum, And all of these have the same initial momentum, right? They're all moving with the same speed and the same mass towards the net, okay? So you start out with a momentum that's positive, all right? When you get to the net, here, I'll use a ball. When you get to the net, right, if it just drops over the net, okay, your direction hasn't changed. So when you do final minus initial, you're actually subtracting off something, okay? If you hit the net and stop, then you just have the same amount of momentum as you started with because your final momentum goes to 0, okay? If you hit the net and bounce back, you need enough impulse to not just stop the ball, but also change its direction and send it back with a particular amount of speed. So the bounce back is the most amount of impulse that you need, so the most amount of force over time. The stopping is the middle, and then dribbling over to the other side of the net is the least, okay? So that's gonna be A. Let's try a problem, and I will set up this problem. So we're gonna drop a rubber ball on a hard floor. I didn't have one. Okay, it's a rubber ball. So we're doing a problem on this thing, okay? So we have a 100-gram rubber ball. It's dropped onto a hard floor, or this table. Just before it hits the ground, let's say it has a speed of 6.26 meters per second going downward, okay? The force that the floor exerts is shown below. And why is the force positive? Which way does the force point? Yeah, because you have a velocity down. Then when you hit the floor, the floor pushes up on the ball. And then what do you expect to happen as it leaves the floor? Velocity points up, okay? So you're gonna start with a negative velocity and end with a positive velocity. So we just wanna do our before and after. So we need some accounting for before and after. So let's say before and after. And we can draw some little pictures. So before, let's say we have the floor right here. And I've lost it. Here's our floor. Before the collision, we have velocity initial, which is equal to 6.26 meters per second. Let me just duplicate this over here. After, we're gonna have a velocity final, which is probably what we're figuring out. Yeah, that's what we're figuring out. With what speed, okay? So, it'd be nice if this were more even, but cool. So what do we need to figure out? Well, we know that our initial momentum should be mass times our velocity, but what are we missing? Because we know that our equation is change in momentum is equal to impulse. So our initial momentum is just mv naught. Our final momentum is just mv final. Okay. So we have that. So we have this. That's just final minus initial. What do we need to finish this off? How do we get impulse? Right? So we're gonna have to figure out what the impulse is, which means we're gonna have to figure out this area. Would that be pretty easy to do?
Mm-hmm.
How do we figure out this area? There's some unit issues here, right? But what shape is this?
Triangle.
It's a triangle, right? So because this is a triangle, we know we need our impulse is equal to 1/2 base times height. Okay? What's our base? 8. Okay, 8 what though?
Milliseconds.
Milliseconds. What does milli mean? 10 to the what?
10 to the negative 2.
Let me try again. -3. Yeah, 10 to the -3. 8 times 10 to the negative 3 seconds. Remember, everything has to be in seconds and newtons. And then what's the height?
300.
300 newtons, okay? So that means our impulse should be 1.2 kilograms meters per second, or you can also write that as newton seconds if you feel fancy and you want to have a slightly different units. But remember, newtons are kilograms meters per second squared. So if you do newtons times seconds, that's just kilograms meters per second. Same thing, okay? So this is our impulse, that's what we're calling it. So impulse, let's just rewrite this, is equal to final, which is that's mv minus mv initial. So if we want to solve for v final, that's just going to be impulse plus mv initial divided by m. So we have 1.2 kilograms meters per second minus 100 grams. What is that in kilograms? 0.1 kilograms. Our velocity is 6.26 meters per second. What do we need to do with that velocity? Is it positive or negative?
It's negative.
It's gonna be negative, right? So we wanna make sure we actually put the negative in there. Let me move this over so I have space for a negative. So that negative means, so look at this. Because it's changing direction, our impulse has to add to this, okay? So that means we end up with something. Did I mess that up? That should be positive. Okay, we're adding. Never mind. So we have it's subtracting. I did the negative twice. So when we rearrange this is a plus, but you have a negative from the sign. So you still subtract off from the impulse, and then you divide that by 0.1 kilograms, and that should give us are we expecting a larger or smaller speed?
Small.
Smaller, because you're subtracting off this term, okay? So that's going to give us 5.74 meters per second. Sorry, I misspoke on the first part. You have an impulse, but you're subtracting from it. Okay. Any questions on this? So we start from impulse momentum theory, right? Impulse momentum theory is this equation. We calculate our momentum from our initial and final velocity. We calculate our impulse, in this case, from our graph, and then we just do some algebra, okay? But this thing right here is called impulse momentum theory. That is the equation that we're starting with. Yes?
So I know we went negative, would it ever not be negative? Like, I'll drop it from like said height and it bounces a little bit higher or a lot higher? It would have to be something that's like.
So for that to happen, you would need like some sort of push from the floor.
Or I would have to throw it harder to make it bounce.
Throwing it harder doesn't. Yeah, it would have to start with so dropping it. You have to start with a zero velocity, so you can only get as much velocity as you can get from gravity from here to here. If you throw it, you can start with a higher velocity, but pretty much you're not going to have a situation, thanks to conservation of energy, where unless your floor exerts like more than just, unless your floor is active instead of passive, you're never going to get a speed coming up that's higher than the speed going down. Yeah. And so that's more of a conservation of energy issue, but if you had like a floor that had like some sort of spring loading that's got like a motor in it that like pushes at the same time, then you could get it to be higher. But I mean, you can just try that with anything. You bounce something off the floor, it's only going to go to the same height or lower unless you have some sort of special floor. Okay. This is actually the reason that if you do any kind of like gymnastics, or you have like a trampoline, right? You're still not gonna, so when you're jumping on a trampoline, you're interacting with the springs from the trampoline to get higher and higher, but that requires energy from you. So a ball doesn't have the ability to do that, but if you had something that could actively get more energy out of the system, then you could. Yeah, that makes sense? Okay, let's try another problem. I'm gonna have you guys work on this one for a little bit, and then we'll go over it in about 3 minutes.
Did you? No, I know because math.
All right. And that would just be cool. Let's talk about this guy. So we always want to start with impulse and momentum theory. If it's an impulse and momentum problem, we start with this equation. And this, oh,
See, that's what I did.
that was weird. And this equation looks like J is equal to delta P. And if you want, remember P is momentum, so that's going to be J is equal to MV final minus MV initial. So where are we gonna get all those things? Well, we know that our momentum initial and momentum final we're gonna be able to get from this graph, right? Because we have the initial and final speeds. So our initial speed, V initial, let's see, that's going to be minus 3 meters per second, and our V final, that's gonna be 3 meters per second, okay? We also know that our impulse has to be equal to the area under this curve. So impulse has to be equal to the area under the curve, and the area under the curve is going to be 1/2, in this case 36, right? So base times height times delta t. So our impulse we can actually write as an equation, right? Because we know the equation of a triangle, okay? Just for the sake of, normally we do these things symbolically, but just for the sake of it, let's do it numerically because that's an option too. So how do we figure out our initial and final momentum? So our initial momentum, that's going to be mass times velocity. What's our mass? 0.6 kilograms, okay? And then our velocity is negative 3 meters per second. So we can do that in our head, hopefully. That gives us negative 1.8 kilograms meters per second. Okay, our final velocity is the same thing, but it's positive, right? Because it's just 0.6 times positive 3 meters per second. So we get 1.8 kilograms meters per second. So when we do our change in momentum, right, we end up with our final minus initial. So that's going to be 1.8 minus negative 1.8. So that gives us positive 3.6 kilograms meters per second. Okay, so if we want to rewrite this just as it was, we end up with this is equal to 3.6 kilograms meters per second. But we also know that J is equal to 1/2 36 delta T, which is equal to 3.6. I'm gonna drop the units just for ease of use, but you know that this should have the same units also, okay? So this is written specifically so you can do it without a calculator. You end up with delta T is equal to 2 times 3.6 divided by 36. And that should give you 1/10, which is 0.1. So this should give you 0.2 seconds. Okay? And it all comes from knowing that 1, impulse is equal to the change in momentum, and 2, impulse is also equal to this area under the curve. Right? Any questions on that?